Today we will solve the problem 6.7 of Griffith third edition Introduction to Quantum Mechanics. The problem 6.7 consists of two parts. We will solve one by one. That is, consider a two particle of mass m1 and m2 in one dimension that interact via a potential that depends only on the distance between the particle, that is v of modulus x1 minus x2, so that the Hamiltonian is h is equal to minus h cross squared over 2m1 delta 2 over delta x12 minus h cross squared over 2m2 delta 2 over tx 2 delta x2, sorry, plus v of modulus x1 minus x2. So acting on a two particle wave function, the translation operator would be t a psi when t a act on psi x1 x2, it will translate from the position x1 to x1 minus a and x2 to x2 minus a. We have seen this in detail when we are dealing with the translational symmetry, that is in theoretical lecture. The section A is so that the translation operator can be written as t of a is equal to e power minus ia over h cross p, capital P, where capital P is equal to the p1 p2 plus p2, that is momentum of the particle 1 and momentum of the particle 2, that is the total momentum. First we have to prove this. Before going into the two particle system, translational operator in two particle system, we will see the some fundamental concept of translational operator in one particle system. When translational operator T of A act on psi of x, it will get shifted to translated to psi of x minus a. From the Taylor series, f of x minus a can be written as summation over n equal to 0 to infinite 1 over n factorial minus a power n tn over tx n f of x. So, same thing, you replace it for psi of x minus a. So, this can be written as from Taylor series 1 over n factorial. Of course, we have summation minus a power n tn over txn psi of x. Now, we know very well that the momentum operator by definition is equal to minus I h cross t by tx. You bring this I h cross to other side, then this will become I over h cross plus I over h cross into p. So you take the power n both side. So now you can see this tn over txn can be replaced by this. So that's what I have done. Then another interesting thing is, see, after replacing this, you got this term. You know very well, e power minus ix is equal to summation over n equal to 0 to infinite minus I power n xn over n factorial. Here you compare this and this. So you have n factorial, you have minus I power n, minus is there, I power n is there, and this a over h cross into p can be taken as x. So this can be written as e power minus ix. So here x is over h cross into p. This, of course, we have psi of x. So naturally, here the translational operator is this one. If you compare first two equation and this one, you can see when translational operator act on this, you are getting psi x minus a. So psi x minus a. So that means this term is translational operator. When it acts on psi of x, you are getting psi of x minus a. So this is the translational operator for a single particle system. Now we will move on to two particle system. And now we will see what will happen when this translational operator act on two particle system. As given in the problem, when the translational operator act on psi of x1 and x2, it will gives you psi of x1 minus a and x2 minus a. Now we have seen from the Taylor series expansion, psi of x minus a is given as this. So summation over n equal to 0 to infinite 1 over n factorial into minus ia over h cross p cat, that is momentum operator whole power n multiplied by psi of x. So here it is a two particle system. The translational operator act on x1 as well as x2. So for x1 you take this. The particle 1 is at momentum p1 and particle 2 is at momentum p2. That is 1 over n factorial. This I am writing as it is. I am replacing p by p sub 1. So whole power n, and summation over 1 over m factorial, the another particle 1 over m factorial minus this same thing minus ia over h cross p sub 2 whole power m multiplied by psi of x1 and x1 and x2. Now you take this. Already we have seen from Taylor series expansion, this e power ix can be written like this. So this can be written as e power I minus I a p1 over h cross. So what about this? Remember that m is only running index. You can take p, q, r, s, whatever may be. So this also equal to e power minus I a, except here you have p2 over h cross. Now if you combine both, remember that p1 and p2 commute. So you can combine. So this will become e power minus I a p1 plus p2 over h cross. Of course, you have the you are multiplying by psi of x1 x2. So now you can cancel this psi of x1 x2 here and here. So this translational operator will become this exponential term. Here P1 plus P2 is total momentum. So I am rewriting this exponential term as e power minus ia over h cross P, capital P. So this is the translational operator for two particle system as we are asked to prove it. So we have proved it. Then we will move on to the next section. Section P is so that the total momentum is conserved for this system. So the Hamiltonian is given for this system is minus h cross squared over 2m1 delta 2 over delta x1 2. Same thing for particle 2, and this is the potential. So potential depends only on the depends between the position of particle 1 and 2. Now we will see the what will happen when translational operator act on this potential. So when the translational operator act on this potential V, which is equal to x1 minus x2, can be written as V of x1 minus a, because this translational operator translate the position from x1 to x1 minus a. Same thing will happen x2 minus a. So now you can see if you subtract this minus of minus will become plus. So this minus a and this plus a will get cancelled. You will get v of x1 minus x2, modulus x1 minus x2. So translational operator does not affect the potential. Potential is preserved under translational operation. So uh, you can conveniently ignore this because there is no change in the potential. Now we will see about the kinetic energy. Kinetic energy basically depends on the momentum p squared over 2m. So let us say by definition h prime, we are taking the translated Hamiltonian, that is h prime. This is not perturbed Hamiltonian, so you need not confuse this. Is equal to d dagger h t, because this is unitary transformation. Unitary transformation preserve the norms, we know it that. So this will be equal to h prime is equal to h. So naturally you take h is equal to t dagger h t. Now multiply both side by t. See, remember that you are not supposed to change the order of the operator. So t comes left hand side in the left, and similarly t comes in the left hand side of the left side of the equation. So you know, since it's a unitary operator, t is a unitary operator, t dagger is equal to 1. So th is equal to ht, uh, which can be written as ht minus th is equal to 0. That is h and t commute, which is commutation of h and t equal to 0. That is translational operator will not affect the Hamiltonian. So we will see what will happen to the momentum. We have seen that the translational operator is equal to e power minus ia over h cross p. Now let us take this small translation delta, that is t of delta, since this delta is infinitesimally small. So it can be written as e power minus I. Instead of a, I am using delta over h cross p. So using Taylor expansion, this can be written as 1 minus I delta over h cross p, and plus it will go on delta, higher order delta term I am ignoring because delta is very small. Delta squared is very smaller. So I can take only the first two term. I can approximately take the first two term. Then just now we have seen that h and t will commute. Here I have taken h and t of delta, infinitesimally small translation, which is equal to 0. So I am taking t delta, I am taking only first two term, 1 minus I delta over h cross p. It is well known that this one is a number which will commute with h, so you can remove it. And the next term minus I delta over h cross is a constant. This multiplication factor I am taking outside. So remaining thing is h, commutation of h with p, which is equal to 0. That is h and p will commute. That means according to the generalized Ehrenfest theorem, the total momentum is conserved because h and p are commute to each other. Uh, so we have proved the second one also. Thank you very much for watching my video and supporting me continuously. Thank you very much.